of the last lecture, and this lecture will be uploaded probably tonight or tomorrow. It will be on the YouTube channel, and also in the Drive you can watch it. All right, we continue our discussions about the scaling equations. This is rescaling the stellar evolution equation are important because, as you remember, we say that this chapter is about main sequence star, and main sequence star, they have many similar properties, like the mechanism of the energy production inside of them, and also, but in other point, in the other point of the view, they have a different size and different temperature and different range of luminosity. So it means that it is possible, it is needed to rescale the equations to find the similar results for all the stars in this range in the main sequence. So if you remember, I show you that the picture of the three clusters of the star, which young, one old, and one is the other global cluster similar to the old one. And there is one open cluster, one more compacted, and the blue one is the young one. So as you see from the luminosity, from the pictures, the luminosity is different, but all of them are actually existed in the main sequence. The problem which we studied in this chapter was that we want to find the ms10 of time, so the time which one star in the main sequence needs to turns to the red giant. This is what we want to calculate. Okay, the rescaling mechanism was that we try to find something like relay equations which be in the correct units, and they only contain the main parameter like the mass and the radius. The first equation which we started is the mass distribution equations. I want to little go in the detail of what was these mass equations. So you have a star with the radius r, if you see here. So this star has a density functions of the radius r actually. So if the star finally reach a final size, you see even it's not a real sphere, because if you reach the radius r, so for example, the mass which is contained inside this inner sphere is given as a function of the r, like mr. You can say that mr is 4 pi, yeah, integral of from the 0 to the r of the density functions, which is a function of the r, but to not be confused with the different r, I use the r prime here. R prime is any coordinate of the integration which can change from the 0 to r. So this is actually the expression for the mass, and this is nothing just the Gauss theorem. So you remember the Gauss theorem in physics 2. Gauss theorem is about the flux of electric field, but here we have the same for magnetic field, for gravitational field, as well as you can have this for any other vector fields. All right. So to make this equation rescaled, we can say that we can talk about the mean density. So the mean density, which we can write by average of rho, or in the more common form, we write rho bar. Rho bar is actually the mean density is given by the total mass over the total mass over the total volume. So volume of the sphere, the total volume for the star is 4 pi r cubic over 3. This is the, so you can say immediately here from here that the average density is scaled as m over r cubic. You are not very understanding, you are not very much in the understanding why we are doing rescaling. Actually, this is the because when you want to solve the equation numerically, you cannot set the radius of integration, for example, the real radius of the star, and you cannot use the real density for the star because the program will be divergent. You know, you will deal with the number like 10 power 8, 10 power 10. And so it is better to write the equation in dimension less or in the dimension less units. So to make that, you have to write the rescaling. So now, if you think about the density of at any distance, I can tell you that dividing the density at any distance to the average is dimensionless. Is a dimensionless. I mean, it's dimensionless. So there is no dimension for if you divide the density over the average density. So I mean, if you have an equation, in this equation there is a rho or p, it's better to divide this equation by some proper quantity to make this dimensionless. All right. So mass equation, you can scale it like that. Just if you have anything like density, just if you have anything in the density in your equations, better to change rho or by somehow divide rho by the average density, so the quantity will be dimensionless. What about the other equation? The other equation is the ideal gas. So ideal gas equations is P is rho kT, PV is nRT actually. Yeah. The second equation is PV is, you know this equation, nRT, the ideal gas equation. Or in other form, you write sometime like nkt, kbt. N kb is the Boltzmann constant times T. Okay. You cannot use this equation very simply in the stellar revolutions. The things which you need to do is that you have to write in terms of the rho. This equation should be written in terms of the rho. How you can write that? You can talk about the average mass and you can talk about the average density. So, and you can talk about the core pressure. So to make this equation dimensionless, something you have to do. So P should be scaled like the P over some quantity which we call it P core is a constant. Okay. Rho, you know what is happened for the rho, and volume, you know what is the volume is scaled like r cubic. So there is nothing about that. Be worried. And temperature is scaled. Temperature is scaled like temperature over the temperature of the core. Temperature of core is the temperature at the center, and P is the P. C is the P at the center. So using these transformations and by remembering the relation between the rho and m, you can easily say that the ideal gas can be scaled like, if you just simply scale it P to PSC, and PSC is proportional to rho bar TSC over mu. Mu is the chemical energy. Okay. So if you have a equation with P, just scale it that. So just change it P in the equation, not change it, divide this equation by central pressure, make the equation dimensionless, and divided the rho. But you have to remember the relation between PSC and rho. Divided the rho by the average rho, and divided T by central temperature. That makes your equation scale independent. For example, the considerations which I told you can be used to rescale the hydrostatic equilibrium equations. One of the other equations in the stellar evolution was hydrostatic pressure equations. You know that if this is a star and if you're standing at a distance r, so the density here is rho r. Okay, so if you consider a shell, a region between two r, I mean r to r plus delta r, a region between that, dr, r plus delta r. So the mass which is enclosed between these two spheres can be easily calculated by dm. dm actually is rho. Yes, dm is rho. dv is 4 pi r square. dr. The self-gravitational energy, the self-force between the mass between these, which is mr. So mass in the radius r is mr, and the rest of the mass, which has a density, leads to the equation. So you have a equation, the gravitational equation in the gravitational interaction between them. The component r of this gravitational energy is minus g. The mass at the distance r multiply to density over r square. So this is the force. This is the force. And force, from thermodynamics, you can say that the pressure is force per area. Pressure is force per area. So if you remember, the pressure in thermodynamics was any pressure like hydrostatic pressure was force per area. We have to correct these equations. So I will tell you why, because we have to first say what is the relation between pressure and the force, and then reach these equations. Okay. All right. Let's say. So we want to find the amount of the pressure which this shell makes, and this pressure is called hydrostatic pressures. So we remember the F, the pressure, the differential of the pressures is the differential of the force over the area. The area, I can call it delta A, okay? This is the area of the where the component of the force will act on that. The area is 4 pi r square, 4 pi r square, And the force is actually dF is minus G, yes, G M dm over r square. All right. This is the equation. Looks like very complicated. Then you write this dm like rho times, you see, rho times 4 pi r square dr. All right. So then, as you see here, this 4 pi r square will be cancelled by this factor, huh? But this cancel 4 pi r square. They will cancel. So your equation will be minus G M rho ER over R square. Those derivations maybe I will ask you to do for exam. Okay. Then the gradient of pressure is dPdr. So finally dPdr, this is the derivation of the hydrostatic equations. dPdr will be minus G M rho over R square. All right. Still you have rho here, you have a mass, which is a function of R. So mass can be scaled like mass over total mass. Density will be scaled like density over average density. All right. What about the R? R will be scaled like R over total R, or the size of that. And what needed more? The pressure. Pressure will be scaled like pressure divided by the central pressures. So by these considerations, you can show that, finally you can show that it leads to the relation between central pressure and the average density and those things. So finally you can show that the central pressures looks like depends on the M, should be scaled like this, like that. And pressure should be scaled P over PSC. And this is the PSC. I mean PSC will be here. PSC. From the consideration of the ideal gas scaling and hydrostatic pressures, you can show that the PSC, which comes from the, from the hydrostatic pressure, we have this relation. From the thermodynamic, we find that the P can be scaled like that also. So just consider these two relations, this with that. Then you can see that those two expressions should be equal to each other. M rho bar over R should be rho bar TC over mu. So it gives you TC. TC will be proportional to the M mu over R. All right. Any questions you have? All right. What about the other equation? The other equation which we left for us is radiative diffusion equation. These very complicated expressions you see in radiative diffusion equations, you have a luminosity, you have a Stefan Boltzmann constant, the radius, temperature as a function of R, gradient of temperature, density, and you have a opacity also. So it is difficult because opacity cannot be easily scaled to anything. But we will assume that for many stars, because of the electron scattering process, the kappa is constant. And then we suppose that for the stars which they have, their mass is greater than the mass of solar systems, or in the order of solar systems, you can scale equations. Basically, still you can scale the equations. To scale the equations, what we do is that we have to think about the equation and think about what kind of the quantity you can set here to make this equation dimensionless or scale independent. The process which you can do is that as following. So you have a luminosity. So I suggest that the luminosity can be scaled as the following. The technique is that instead of the R, we think that the R can be scaled like R square. R square is the radius of the star. Sigma is a constant. T could be scaled like T cubic. Rho can be scaled like rho bar. Kappa can be constant. We should not be worried about that. T again will be scaled like Tc, and R will be scaled like R. So if you see one R will be cancelled by that, so it means that if you divide L by the following quantity, you always can make these equations which involve L dimensionless. All right. So if you have an equation, just divide L by this quantity. This is, you can call it L star, for example. Then the expressions, I mean, L over L star is dimensionless. Will be dimensionless. It will be just number. I mean, it will be number like n, like 1, like half, and etc. No unit for that. and you can integrate the equation easily. You had the relation between rho and Tc. So if you use that equation, you remember that the rho bar could be scaled like m over r cubic. You remember? Just a few minutes before. And Tc can be scaled like m over r multiply mu. So if you just substitute these expressions, finally you can say that the L can be scaled just by dividing any quantity which we call a luminosity by this quantity. This is L star. Different representation for L star. We have a different representation actually. So what we obtain now is that we show that Tc could be scaled, T could be scaled as Tc as a function of r, m, and mu. And L also can be scaled as a function of, again, m, r, and mu. L star. So you got the point. The idea is that you have a machine or you have an input. So your input is r, m, and mu. And you scale the equations, you're rescaling equations, rescaling, okay? Scaling any differential equations which you have, evolutionary equations. Then the equation will be dimensionless, so there will be no units for them. No unit. They can be integrated easily, so you can integrate it then. You can integrate the equation and find the solutions. Mainly, we can find m as a function of r, for example. One of the important things. Or pressure profile, for example. R means okay. That is the first part of today's lecture. There is remainder one more equations. It is not it is actually auxiliary equations. The auxiliary equation is that it's called energy generations. Luminosity is related to the density of energy which produces it at the distance of r. So there is still one equation which you need to be scaled, and this equation is the equation for energy productions. So the differential of the luminosity or gradient of luminosity is given as the following. The aim is how to scale this equation, how to scale the E. So actually there is a model for the E. In many cases, E can be considered as a function of the following. So you have a square of the density mass here, for example, times the radiation temperature, nu. This is a function of R. So you know how to. Nu is exponent actually. is exponent, it looks like the, can I write V here instead of nu, because nu is difficult to read it. V. This equation actually looks like the Stefan Boltzmann equations. It looks like Stefan Boltzmann equations, and we want to see how to scale these equations. So to scale the equation, you have the information about L. You already have the equation for, so the process, what is the process? The process is that you change this equation to normal ratio between L and R. So you remember the L was proportional to the, you have the information for L. L was previous time. L was scaled like RTC4 rho bar. Yeah, this. So we can keep it in mind is expressions. And what about there? Here I can say R square. Rho, we can scale it like rho bar. And T, we can scale it like TC power this exponent, V. Oh no. Okay, now what we can do is that we substitute the expression which we have for L. If even now, if you simplify this equation, at so far you get L is proportional to R cubic rho bar 2 rho bar square over TC power V, or no. Yes? The next step, this is what you have now. The next step is that you use the relation for rho bar. Rho bar was M over R cubic. Yes? And TC was MR. And TC, because TC was MR, we find it in the previous slide, MR times mu. So, and you have the, so just from now, you can say that L is proportional to, you have M square here, you have M power nu, so will be, and you have R cubic here, you have R cubic square here, so will be 6, 1 plus 7, so will be minus 4. But here is V, sorry. Will be 6, so will be 3 minus V. Minus 3. Just working with the powers here. Minus 3 minus V. What about the M? So M will be a scalar. This is M power mu V plus 2. And mu will remain like mu power V, the chemical potential. Okay? So you know before the previous slide showed that L should be equal to, from before we know that L is proportional to M cubic mu 4, I think. Yeah, mu 4. How I can make this expression correctly written, these expressions, when I have a two side of this equation, the left and right side. Okay. I want you find for me here the V, the possible V here. From here you can find R, finding the R. So find the R from here, from this equation. If you find R from this equation, R will be proportional to the you have to take a power -1 over 3 plus v of what? What you will have here will be m. 3 minus 2 is 1. 1 minus v. 1 minus v. And you will have mu here, which is 4 minus v. All right. And you can take the limit of, you can take this power, and then you will end with this expression. You can show that in this case, the equation can be scaled if you scale the mass like that. V minus 1 over v plus 3 and mu power v minus 4 over v plus 3. You can scale the temperature by this because you know what is the relation between temperature and density and those. So temperature was scaled by Tsc. Tsc was proportional to mr over mu. You know what's the technique? The technique is that I want to remove the r actually. If you substitute the r here and just working on the powers, you can see that the Tc will be proportional to the 4 power v plus 3 and mu power 7 power v plus 3. One consideration before I continue, I want to discuss something about these powers. What does it mean, those powers? You know, for example, R, you know, R was scaled using this, like m power n, and mu power m. N is nu or v minus 1 over v plus 3 or nu plus 3. If you check these functions as a function of nu, when nu is 0, so it gives you something like here, negative number 1 over 3. When nu is very large, what happened for these functions? Can you tell me? When nu is very large. When nu is here, for example. What is the n for large nu? For example, Bayan, you can tell me that, Bayan, what is the limit of n when nu is very large?
Maybe it's 0.
No, maybe no, maybe no. Limit comes like a number. Don't say maybe. When nu is infinity, what will be n? The limit of n?
It will be infinity.
No, 1. When nu
1.
Yes, taking the limit of this, limit x minus 1 over x plus 3 when x goes to infinity, From numerator remain just v, from denominator v over v will be 1. So it will be v here. It will be also intersect with the axis like here. And when nu goes to minus infinity, what is this? So n will be 1. When nu is minus infinity, what's happened for these functions? N will be what? Here. I mean, how I can, this is the way to plot the functions. I want to plot this function as a variable when the variable is v. When v is 0, I have this point. When function is 0, I have this point. When v is large, I am here. When v is large from left side, what is n? Limit of v minus v plus v plus t. When v goes to minus infinity, what is this limit? 1, huh? You need to review the calculus. It is, yeah, but not after me. Okay. All right. How I can plot the functions? And there is a one value for the v which is very dangerous. What is the v which will be very dangerous? When v is minus 3, huh? Yeah. This is very dangerous because when v is minus 3, n will goes to what? To infinity, huh? So the functions will be like that, huh? Lucy, sorry. Let's plot this with a different color. Without using the computer, you can plot this function. So your function will comes like here, goes here, and then goes there. Oh. Did this function ever will cross this line? Do you think you can exit this line, go far from this dash or no? This is the dash line. Dash is 1. This is n. Huh? What about the m? The scaling power m will be nu minus 4, or v minus 4 over v plus 4. Huh? V plus 4. Okay, give me an idea about how I can consider the limits for that. I mean, what is the maximum, minimum of this function, and how I just analyze I needed to, you know, this is the qualitative behavior of the function. What you can do is that you can consider the something like that. When v goes to infinity, what is the functions? The function will stop below the line. Huh? Why? Why never exceed this number? This is 1. Oops. When nu is 0, it comes like here, somewhere here, minus 4 over 3. When nu is minus 3, again the problem will start it. You have a asymptotic, you have a divergence term, huh? The scaling component will be diverged here. So, and when nu is 4, somewhere here, you will cross the line, cross the axis. This is the behavior of functions, huh? The function will comes like that and goes, oops. Goes like that, huh? And never will touch this line. So this is the water score. Okay. Scaling scaling power are very important. Scaling exponent, they say exponent. The scaling exponents in the stellar evolutions are very important, as you see. All right. And you can also finally also make the same analysis for TC. So let's go to next slide. So TC scale it finally like m power something. What is this? I say, for example, m n prime, for example, huh? And mu power m prime. Or n double prime, huh? Or what is there? Because a and no, n is for mass, so you will be maybe confused. So I say R, okay, and B. This is the exponent. So A is the exponent of the scaling temperature. The exponent of the M actually is 4 over this. And scaling for the, when the power is mu, is 7 V plus 3. The quality behavior of the function are the same. Still you have a asymptotic discontinuity here when it is -3. When you have a 0, it will go like here or here. It depends. Which one is for A and which one is for B? This is for A or this is for B? This point is for A or this point is for B? Here you have B. Before, tell me one thing. When V goes to infinity again, for the large, very large energy diffusions versus the temperature, what is the behavior of A and B when V is infinity? Who want to talk about this? Okay, sure. When V tends to infinity, what is A and B? Okay, A will be 0, and B also will be 0. Which one is for A and which one is for B? This is A or this is B? Which one?
The first one is A and the second one is B.
Yes, bravo. This is for A and this is for B. So you can tell me that this will be graph for A, huh? And this is graph for B. But when you are at very large regime of energy diffusions, what does it mean, this term I say? In large regime of energy diffusions. What you understand from that? In the large regime of energy diffusions, or energy diffusion large regime, the exponents for M and mu both will be the same. I mean, A will be approximated equal to B at very large large regime of energy diffusions. Writing by this is make your speed in a reasonable, I think, way. Because if you write on the whiteboard, real whiteboard will be very fast, and we lost the meaning of the equations also. Look at that. To make a scaling of the energy diffusion equations, we use the information which you already know about rescaling on luminosity and temperature and density and so. And then we find two very important exponents. One exponent gives you the power for Tc, actually. Tc comes like a function of m and mu. And the other equations gives you the scaling for r as a function of m and mu. And we talk about the different behavior of the functions. At very large energy generation rate, when V is infinity, A and B will be 0. So Tsc will be a scalar like 1. For large regime of energy generation, you don't need to be worried about the scaling of the temperature. What does it mean? Can somebody say? What does it mean? In the large energy generation regime, we don't need to scale the temperature. What does it mean? What you understand from scaling so far? Can you tell me what is scaling? Last lecture, this lecture, and next lecture will be again about the scaling of the questions. What is the meaning of the scaling? I explained that in the previous lecture. I say we want to use the same set of equations for the system which they are looking very different in the scaling or in the size. And today we find that at very large energy generation rate, scaling for temperature is not important. It means that you don't need to be worried about the scaling of temperature. But I want you make a physical description for that. What is the physics for this? You can think about it later. Okay, we summarize what we did it. We summarize what we did it. We trying to rescale any equations. Finally, you see that we want to write everything in terms of m and mu. As you see here, L finally scaled. I mean, if you divide anything which have L by this quantity, you can be sure that you will get just a number, yes, without any units. You can also say that the R will be scaled if you have R, and if you consider the energy generation mechanism, then n and mu, so you have to write this as a function of n and mu as a function of m. We talk about what is the n and m. They're a function of v actually. And Tsc finally will be scaled like m power a. A was a function of v again, and mu function of b. And we talk about all of them. So both all of m and m, a and b are considered functions of what? What was the argument of the functions? The argument of the function was m, n, and a and b were function of what? Function of v. V was the exponent which appeared in the energy generation equations. We can use this dimensional analysis or scaling in different ways. One is to ask how the luminosity, radius, and core temperature of stars which have the same compositions depend on their mass. Or you can use that about one star just with fixed mass and think about how the chemical energy will be changed, for example, when the burning hydrogen to helium process is happening. In lecture, we will go to use this equation for two purposes. First purpose is that you want to consider low mass regimes. Low mass regimes are the stars that their mass is in the level of the mass of the sun, and proton-proton change dominated. So for such systems, V or nu is 4. V is 4. And higher mass when the CNO cycle dominated. For them, nu is 17. Why we know these 4 and 17? Those come from some data analysis, actually. There is a warning note here that scaling relations should be written, for example, when they have a temperature, should be written in terms of the core temperature. We don't talk about the effective temperature here. Effective temperature is the temperature which characterizes the one layer of atmosphere of the star. We talk about that in first chapter. If you need something which involves the effective temperature, then you have to go through the luminosity equations and drive the effective temperature scaling through the Stefan-Boltzmann relation. So I give you the task. The task is that you have now the luminosity scaling M3 mu4. Yeah, you can go and give me the scaling of the effective temperature which comes from these equations. T effective 4. I want you make the same effect scaling analysis for the effective temperature from this. So you have a scaling for that. You have a scaling for this. Where is that? You can see here. R is a scalar like this. L is a scalar like that. And give me what is scaling for the effective temperature. So this is a very easy task. I ask you, do it for me, but for next lecture. So at the beginning of next lecture, I will ask you. I will make a question about this from you. All right, we are going in the direction to talk about the stars with big mass or lower mass and higher mass. So I will keep it for the next lecture. This. Do this as a task, as I told you. Make a scaling analysis, rescaling analysis for T effective. All right, do you have this lecture was a little hard for you, I see. Not very much. One is joining very late. Why? Please don't chat. I asked the question and you write here for me. I don't check at them. So just please turn on your microphone and tell me if you know the solution of any of the questions which I will ask you. Okay.